All right, now in the previous two sections, we showed that row operations can be used to solve a system of equations. Just to go back here, remind you, we had this system of equations here, and we changed it into an augmented matrix, and in a fashion much simpler than previously, we were able to come up with a solution. But what we didn't explain or go into much detail was why we chose this sequence of row operations. So that's what we're going to talk about here. It turns out that this form that B is in is a special type of form. It's called reduced row-echelon form. And in the last video, I noticed that you have this stair-step pattern of ones beneath which you have zeros. And that's characteristic of this special form called reduced row-echelon form. You always want to get your matrix into such a form, and then you can easily solve the corresponding system of equations. All right? Now, here is the definition of reduced row-echelon form. Number one, if there's a row where every entry is 0, then this row lies below any other row that contains a non-zero entry. What does that mean? Well, if I have a matrix like this, I can have rows that are entirely 0, but they have to be at the bottom. Okay? I could have one, I could have more than one. Okay? But if I have any, they have to be entirely at the bottom. Second specification. If I have any entry with non-zero entries, let me say that again. If I have any row with non-zero entries, the leftmost entry has to be equal to 1. Okay? So, for instance, if this first row, what's happening here? If this first row has a non-zero entry, it's not necessarily the case that the first column has a non-zero entry, but if this row has a non-zero entry, the first non-zero entry must be a 1. Okay? And if for any row I have here, the first non-zero entry must be a 1. All right, let's see the third condition. Third condition, leftmost non-zero entry of a row is the only non-zero entry in its column. All right, so what that means is that all of these ones must be the only non-zero entry in their corresponding columns. So this 1 here must have zeros down here. Okay. Now this entry here, this could be something other than 1 because it's not the first non-zero entry. So I could have, I don't know, something here. I'll just put a star here to denote that that could be anything. However, this rule that I just saw, this rule that the leftmost non-zero entry of a row is the only non-zero entry in its column, that rule means that this entry here, this 1 here, is the only non-zero entry in its column. So I have a 0 here. Okay? Last rule, this is the most complicated one. Consider any two different leftmost non-zero entries. One located in row I, column J, and the other located in row S, column T. If S is greater than I, then T is greater than J. What does that mean? That means the larger rows have leftmost entries that are farther to the right. Let me say that again. The larger rows, the rows farther down rather, have first entries that are farther to the right. Rows farther down have first entries that are farther to the right. So what does that mean? That means in particular that all of these entries have to be 0. Why is that? Well, suppose there was a non-zero entry here. That would mean the first non-zero entry in this row would be farther left than this non-zero entry. But what I just said, the rows farther down have first non-zero entries that are farther to the right. So for instance, I could have an entry here. I could have a first entry here. And these could be anything, because once I have my first non-zero entry, everything is fine. These have to be zeros. These have to be zeros. Okay? And just go on like this. Now notice we have this stair-step pattern of ones. They're not necessarily equal steps. They're not necessarily consecutive columns, but we do have a stair-step pattern of ones below which you have all zeros. All right, such a matrix is called a matrix in reduced row echelon form. And we'll see several examples in this chapter. Okay. Some more notation. If a row has only 0 entries, it's called a zero row. The leftmost non-zero entry is called a leading one. So each one of those non-zero rows has a leading one. And the column that contains the leading one is called a pivot column. Sometimes we call that pivot one, that leading one, we call that a pivot entry. So this one, this one, this one, these are all pivot entries. Pivot entry, this is a pivot entry, this is a pivot entry, this is a pivot entry. Okay, so there's your notation. That's the form. Those are your pivot entries, and so on. All right. Typically, we will use the letter D to denote the set of pivot columns, and those are the columns that have first non-zero entries. So this here is a pivot column. This is a pivot column. This is a pivot column. But I really messed this up. This is a pivot column. And this is a pivot column. So those are the pivot columns. Okay. And the columns that are not pivot columns we'll call by F. Now the F means something. We'll see what it means later. Okay. Let's go down. All right, here's an example of a matrix. Let's check and see if this matrix is actually in row-reduced row echelon form. First condition, if there's a row where every entry is 0, this row lies below any other row. Okay. And we see that's true. We have 2 0 rows, but they're both at the bottom. Second condition, leftmost non-zero entry of every row is equal to 1. If you go along this row, first entry is a 1. Go along this row, first entry is a 1. Go along this row, first entry is a 1. So second condition checks out. The leftmost non-zero entry of a row is the only non-zero entry in its column. Let's check that. This one is leftmost, all zeros, check. This one is leftmost, all zeros, check. This one is leftmost, all zeros, check. All right. Now here it says that the rows farther down have leftmost entries that are farther to the right. That's what this one means. And that's true. This one is farther to the left than this one, which is farther to the left than this one. You can see we have our stair-step pattern, and we're good. All right, the pivot columns are here, here, and here. And then the non-pivot columns are the other columns. All right, let's check this one, see if it's reduced echelon form. First of all, the first check is see, is this in stair-step form? Well, let's look here. Here's our stair-step. Whoops, that's a 5, not a 1. That doesn't work. All right, and that's not the only thing. Here we have a 0 row in the middle. That 0 row is supposed to go down on the bottom. And we got one more thing. This 5 is over here. This 1 goes back here. That's wrong too. Okay, so this matrix is all messed up. All right. So this is the form, and as I mentioned, this form is going to have a particular easy way to find solutions for the corresponding system of equations. First, a couple of theorems. What this theorem says is that I can find a reduced row echelon form for any matrix whatsoever. And that's the idea. And that's good because I want to be able to convert any system of equations into a system of equations in simple form. Right, so what the theorem says is if A is a matrix, then there is a matrix B so that A and B are row equivalent and B is in reduced row echelon form. What this means is that there's always a sequence of row operations that takes any matrix A to a matrix in reduced row echelon form. The proof is actually proof by procedure, and this procedure is known as Gauss-Jordan elimination. Now you've seen the procedure already. Let's go through the steps and see how this works. Let me just explain it in words first, and we'll go back to this example to see how this works. The procedure is really what we did in this example here. So hang on a second. There, all the writing is gone by magic. I wanted to get rid of the junk so we could see this clearly. See what we're doing here. Here's the matrix we started with. And what you're actually doing is creating the zeros in each column and the pivot entries at the same time. So what's the first thing we did? Well, this is the first non-zero entry in the first row, right? It's already a 1, so we're good. We want to make all the other entries in that column equal to 0. So these two row operations were chosen specifically so that this entry becomes a 0 and this entry becomes a 0. At this stage, I have a leading 1 in this row, and I have zeros in every other entry in that same column. Now, what's the next thing I have to do? Well, if I look at the second row, here's the first non-zero entry. It's already a 1, that's okay, but I need to make every other entry in that column equal to 0. Okay, so what he did here was to make this one 0 down here. He didn't turn that into a 0. There's a reason for that. I won't get into that, but if I was going to make this completely reduced row echelon, I would have to do another row operation to make this one be a 0 as well. All right. So now we have this case here where we have zeros in this column. We've got a 0 here. Now the first entry in this row is a -1. I do a row operation to make this a 1. So here we have a stair step. This is almost reduced row echelon form. The only difference is that these guys are not zeros. But I hope you can see that it would not be difficult to do row operations to make those guys 0. Why don't I just do that here? If I took -2 times R2 plus R1, what would that do? Well, that would make this one be a 0, right? I get 1 here. Then I get -2 plus 2 is 0. I get -2 plus 2 is 0. And then here I get -2 plus 4 is 2. And then this stays the same. And then this becomes 0, 0, 1, 4. And then the last thing I would have to do is take -R3 plus R2. Now, why did I do that? Because I want to make this one be a 0. And that would give me 1, 0, 0, 2, 0, 1. -1 plus 1 is 0. -4 plus 1 is -3. 0, 0, 1, 4. Okay? And this guy is in reduced row echelon form. Okay? Now the idea is that you can do the same procedure with any matrix. So rather than going through this proof and this general description, I think the best way to learn about this is just to understand the procedure through looking at a lot of examples. So I'm going to skip this theorem and this proof, which you're probably happy with. All right. Now another theorem that's important for theory is that the reduced row echelon form is unique. If I start with a matrix A and I obtain a reduced row echelon form, I'm always going to obtain the same reduced row echelon form. You can't have two reduced row echelon forms that correspond to the same matrix A. Now I show a proof of this in another video, but again I want to skip this. I think in this first go round we just want to understand the procedures, and the proofs can come later. All right, here we go. So let's see how this procedure works for this system of equations. First step, change this into a augmented matrix. Now, whoops. Be careful here. You have to line up the variables properly. This has x1, this has x1. I really should write the x1 over here. Right? Then my variables are lined up properly. Now you can see that this coefficient matrix here corresponds to the left-hand side here, and this constant column here corresponds to the constant in the equation here. All right, now according to what I mentioned before, what we want to do is create our stair steps of ones. All right, now there's a lot that's not right here. Look, we have a -7 here. We got to fix that. So one way to fix it, we could multiply this first row by -1/7, but there's an easier way, and an easier way would be to take the third row and switch it with the first row. Then I've got a 1 up there. That's a good thing. So that's the first thing that we're going to do here. And as part of the bonus, we get a 0 here, which is something that I want. Now that's not always going to happen, but we're just lucky in this case. All right, so we're well on our way to getting our first row. Let's look at the second row. This is not a 0. That's a problem. We want to make that a 0. The way to make it a 0 is take some multiple of the first row and add it to the second row. Now notice in this case I'm working with the first row and not with the third row. That's typically the way we do things. If you want to operate on a row, typically you add a multiple of a lower row to that row. All right. So, and actually, if I want to eliminate the entries in the first column, I always use the first row. The reason we do that is that it's easy to program a computer to do that. All right. So, question: if I want to make this 5 into a 0 through a row operation, what multiple of the first row do I need to use? Well, if I multiply the first row by -5, that's going to kill this 5 here, right? Because -5 times 1 is 5, and that is -5, and that's going to kill this 5. So let's see one by one how that works. I'm going to take -5 times R1 plus R2 and replace the existing R2. All right? How does this work? -5 times 1 plus 5 gives me 0. -5 times 0 plus 1 plus 5 gives me 5. -5 times 4 is -20, plus 7 gives me -13. -5 times 5 is -25, plus 24 gives me -1. All right? So that's how I get this matrix here from this row operation. What's the next thing I want to do? Well, I want to make this guy into a 0. Remember, I want this to be a pivot column, so I want just a 1 in the first entry. All right? How am I going to make this into a 0? Well, I really only have one choice. If I take 7 times the first row and add it to the third row, then that's going to work. That's going to kill this entry here. So that's the row operation we use here. 7 times R1 plus R3. All right, let's verify that this works. Okay. 7 times 1 minus 7 gives me 0. 7 times 0 is 0. Minus 6 gives me -6. 7 times 4 is 28. Plus minus 12 gives me 16. 7 times 5 is 35. Minus 33 gives me 2. All right? So I check out that this row corresponds to this row operation. So far, so good. On to the second row. Are we good with the second row? Not yet. This 5 needs to be a 1. How am I going to do that? Well, you could try to twiddle around with adding rows, but let's just multiply the second row by 1/5. Okay? That's the row operation here. I'm going to leave the first row. The first row is good. Let's take care with the second row. Second row, multiply by 1/5. I just put a denominator of 5 under all these entries. 5 over 5 is 1, minus 13 over 5, minus 1 over 5. All right, now let's take stock now. What's the next thing I want to do? Well, I want this to be a pivot entry. All right, if this is going to be a pivot entry, I have to have zeros in every other entry in that column. So I'm going to have to get rid of this minus 6. How am I going to do that? Well, I'm going to take a multiple of the second row and add to the third row. All right, so the multiple that works is 6, because 6 times 1 added to minus 6 gives me a 0. Okay, so here's my row operation. 6 times R2 plus R3. 6 times this second row plus the third row. All right, let's see how this works. 6 times 1 minus 6 gives me 0. That's here. Second one, 6 times minus 13/5 plus 16. That's a little bit more difficult. 6 times minus, well, you can use your calculator or something. 6 times minus 13/5 is going to be minus 78/5, and this is 80/5, and that leaves me with 2/5. 6 times minus 1/5 is minus 6/5, plus 10/5 gives me 4/5. Okay, so I verify that this third row here corresponds to this row operation. Now what do we have to do? Got to take care of the last row. All right. Now, nice thing here is that things they're starting to get better at getting rid of denominators. I want to make this into a pivot entry, so I want to make that into a 1. Best way to do that is multiply the third row by 5/2. And that's exactly what happens here. Multiply the third row by 5/2. 5/2 times 2/5 is 1. 5/2 times 4/5 is 2. Good deal. Not quite done. I need to make these guys into zeros. Okay, and to make the first guy into a 0, well, I want to take this first row and use this third row to get rid of the 4. Okay, so I'm going to do the first row, and then I'm going to add negative 4 times the third row. All right, I'm sorry. He worked from second row backwards, so let me backtrack a little bit. He's getting rid of this minus 13/5 first. If I want to get rid of this minus 13/5, I'm going to add 13/5 times the third row to the second row. Okay, so I have add 13/5 times the third row plus the second row. If I do that, the 0, 1 stays the same. 13/5 plus minus 13/5 is 0. 13/5 times 2 is 26/5 minus 1/5 is 25/5, or 5. All right, so I've taken care of this row. One more entry here. Got to take care of the 4. So I'm going to take minus 4 times the third row plus the first row, and that gives me 0 and minus 3. You can check that. So all these check out. This is my reduced row echelon matrix that's equivalent to my original matrix. Now, if you think about what equations these represent, it's very easy to solve. This is x1, this is x2 column, this is x3 column. That first row means x1 equals minus 3. Second row means x2 equals 5. Third row means x3 equals 2. Bingo. I don't have to do any other work. All the work is done by the row reduction, and I have the solution to my system of equations. Okay. All right, here's another example. I'll do it a little more quickly. Again, he has this case where the x1 should be over here. Okay, first column, second column, third column, last column, which is the constant column. You can check that these, whoops, this x2 should go here. That's a 0 there, right? Take care of your variables. Okay, this is these are the coefficients of the x1s. These are the coefficients of the x2s. These are the coefficients of the x3s. Notice the 0 there. There's no x3 in the third equation. Let me make this a little bit more neat. It looks kind of, whoops. Okay, so this one should be x1, and this one should be x2, and then this should be 0. Okay. All right, now what do we want to do? Remember the procedure. We've got a 1 in our first equation as leading entry, so that's okay. I want to make this guy a 0. To make this guy a 0, subtract 2 times the first row, work it out, this is what you get. Next thing I want to do, I want to make this guy into a 0. Okay, to do that, I'm going to subtract the first row and add to the third row. This is what you get. What's the next thing I have to do? First row pivot entry is okay. Let's take care of the second row pivot entry. All right, this 3 is too big. Need to divide by 3, and that gives me a leading 1. That's good. Now I have a leading 1. I want to get zeros below, so I do that by, well, he did a little different order here. There is some freedom in the order that you do. I wish he'd done it the other way, but that's okay. So he has to get zeros in this entire column. So he added the second row to the first row, and he got a 0 here. Then he wants to get a 0 here in this entry. So he does with minus 2 times the second row plus the third row, and that turns out to give you a row of all zeros, which is good. Now we're done because we have our pivot entries, our pivot columns that are all set, and we have our stair-step format. So this is all done. Now the question is, what are the solutions to this system of equations that corresponds to this augmented matrix? Well, let's write them down. This is the x1 column, this is the x2 column, this is the x3 column. So this first equation corresponds to x1 plus x3 equals 3. That's this equation down here. Second row, x2 minus x3 equals 2. All right, so this is the system of equations that we have. How are we going to solve this? Well, notice that we actually have 3 variables and 2 equations. Turns out that I can choose x3 to be anything I want, and I can get answers for x1 and x2. I can rewrite this as x1 equals 3 minus x3, and I can rewrite this as x2 is equal to 2 plus x3. So in fact, I can choose x3 to be anything I want, and I can get values of x1 and x2 that work. So this system has infinitely many solutions, infinitely many solutions. Okay. All right, so here he does the same thing that I mentioned. And so here's the way we write the solution. x3 can be anything. x2 is 2 plus x3, and x1 is 3 minus x3. Okay, so that's another way of denoting solutions in the case where there's infinitely many solutions. All right, one more system. Let's see how this works out. Remember, first step, get the augmented matrix. No zeros here this time, so all of the columns are lining up properly. Pull out the coefficients, put them in the matrix, get the constant vector, put it in the last column. Let's take care of the first entry here, turn that into a 1. Now we can turn that into a 1 by interchanging the 2 rows here. So that's what he does. He moves this up there and he moves that down there. So I've got a 1 in my leading entry here. I want to get zeros in this entry and this entry, so I do them one by one. To get a 0 here, 3 times the first row, add it to the second row, get this result. You can check that this actually works. Okay. Now we want to make this be a 0 in order to make the first column be a pivot column. I'm going to take minus 2 times the first row plus the third row, and that'll give me this one. All right, what's the next thing I want to do? First pivot column's okay. Let's take care of second pivot column. Second row, not a 1 here, so we need to divide by 7. Fortunately, a lot of these divisions work nicely. Okay, so I'm going to divide. Well, all right, sorry. Take that back. He's going to use a different method. Instead of dividing this by 7, he's going to exchange these 2 rows, and the reason he did that was it's easier to make this one a 1 than it is to make 7 a 1. All right, so the upshot is that there is more than one way to get to the final result, but the theorem tells us that the final result will be the same no matter what method we use. All right, exchange these two rows. That gives me a -1 here. I want to turn that into a 1. Okay, so multiply the second row by -1. What's the next thing I have to do? Next thing I have to do is put 1s in the second column. I'm sorry, put 0s in the second column wherever there's not a 1, because this is going to be my pivot entry. Okay, so he's going to turn this into a 0, turns this into a 0 by subtracting R2 from R1 and replacing. You can verify that this works. Then he's going to subtract 7 times R2 from R3 to make this be a 0. Now, fortunately, that gives us zeros here, so we're good. All right. Now, the only thing that we have to do is take care of the leading entry in the last row, and we just need to multiply the last row by -1/5. So here we have our stair step. Okay, and we need to take care of this too. Once we take care of this, once we take care of the 2, we've got our stair step with pivot columns, and we're all good. Now, there's a problem with this. If we try to turn this back into equations, this one's the x1 column, x2 column, x3 column, x4 column. This is the column of constants. How does this last row translate into an equation? Well, 0 times x1 plus 0 times x2 plus 0 times x3 plus 0 times x4 equals 1. That means 0 equals 1. That doesn't happen very often. In fact, it never happens. What does that mean? That means there's no solution. Now, there's no solution to this system means there's no solution to the original system of equations. Now, we've done 3 examples. We found one case where there's no solution. In the previous case, we found an infinitely many solutions. And in the first case, we found a single solution. It turns out that those are the only 3 possible cases. It's supposed to be a 2, I guess. Those are the only 3 possible cases. So you've run the gamut. Whatever system of equations you're going to do is going to look like one of those 3. Okay, so hopefully you're well on your way to be able to doing row reduction.